Well, here we are, guys, scenario 2 on our third and final Excel report of the semester. So let's go ahead and see what we're going to be doing in scenario number 2. For scenario 2, we are going to be talking about binomial experiments. Well, to be called a binomial experiment, we have to satisfy 4 requirements. Okay, and those 4 requirements are that we have to have a fixed number of trials. In other words, we can have 5 trials, but really we should have at least 25 to 100. Or we can even say we're going to do 10,000 trials, as long as we have some finite number of how many trials we're going to have. And then we have to have the fact that each trial is independent of the other trial. So we can think about maybe like flipping a coin. Every time we flip a coin, the second flip has nothing to do with how the first flip turned out. The first flip is heads, the second flip could be heads or tails, just the same. So then also there has to be only 2 possible outcomes. So again, like flipping the coin, we have either heads or tails. If you're answering a quiz, it's either right or wrong. Other stuff, colors, it could be black or white, the answer yes or no, only 2 possible outcomes. Thinking back on when we were rolling the dice, we don't want to think about the fact that we would have 6 possible outcomes. No, that's not the case. It's whatever we want or whatever we don't want. So if we were looking for a 6, then it would be an outcome of a 6 or not a 6. If we're looking for primes, it's either prime or not a prime. So that's what it means by 2 outcomes. And then the probability has to stay the same from one trial to the next. So again, the coin flipping, we have a 50-50 chance every single time we flip. When we're rolling the die, we have a 1/6 chance every single time we roll that die to get that 6 or 5, whatever number it is. All right, so those 4 requirements have to be satisfied to be a binomial experiment. Binomial probabilities come with a lovely formula. Everybody's excited about formulas. So, you know, we're going to be looking at some formulas here. We're not going to have to manipulate the formulas, but we are going to identify the variables and plug in the values that belong to those variables. And we're going to do that in Excel because don't we love letting Excel do the work for us? And when we talk about the binomial formula, we have a lot of stuff here we've never seen before. We have the choose and choose X. We have our P's and our Q's, and then talk about minding your P's and Q's, huh? And then we have the super excited N, and we have lots of super excited stuff going on down here in the denominator. Now, when you guys look at this explanation point in math, it is actually a math function, just like a multiplication or a division or a square root. So in this case, or a minus or a plus sign, our explanation point means factorial. And factorial simply means 5 factorial means 5 times 4 times 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. And then we have, what is this? 4 times 3 is 12, times 2 more is 24, not 21. I'm sorry, not 14. All right, so, and then we have 3 factorial is equal to 3 times 2 times 1. And this also is incorrect, and this is 6. So in this case, you can see what factorial is. I have a joke for you. Knock, knock. Who's there? Orange. Orange who? Orange, you glad I didn't say 100 factorial? I know that was corny, but I was just thinking if I would have done bigger numbers, I would have been reading that all night long. So in other words, what I'm trying to say is factorials can get huge, because if I do have 100 factorial, that's 100 times 99 times 98. So, you know, those numbers can get big quick. All right, so here is our big formula for probability of a binomial experiment. This P of X, let me run up here and grab my highlighter, copy that highlighter and bring it over to this slide. My P of X here means the probability of an event occurring. The probability of, we'll just call it an event for now. And then here we have combinations. And if we look right here, we see that N is the size of the set, where K is the number of selected elements from the set. And you guys are going to see this sometimes notated as a K and sometimes as an X. So where it says kilo in this formula, it says X-ray in this formula, and that's okay. They just both represent the number of items of the set for which we are trying to group. All right, now let's look here. We have permutations of a full set. So these are the permutations. We see the factorial, and then we have the permutations that are left over. And we're going to look at this with some pictures to make it a little easier. And then again, the permutations of the selected set. So let's see what, and on this, we're just going to look at the permutations. So right now, we're kind of picking this formula apart, and we're going to just see what exactly is a permutation. So when we're looking at permutations or at the combination formula for the probability of a binomial experiment, the combination formula is made up of the permutation formula. So you see here we have the permutation formula, and then to create the combination formula, which is used in the binomial experiment formula, we see that part of that permutation formula is in there. As a matter of fact, all of it is the permutation formula except this one little piece where it says x factorial here in the denominator. And we're going to look at that too. You don't have to think too much about all these formulas. We're going to try to show you this all pictorially. All right, so now here, let's look at the difference between permutations and combinations. So here I have 5 objects. I'm going to permutate 5 times. And then on the right, I have 5 objects I'm going to combine 5 ways. I'm sorry, I said that wrong. 5 objects I'm going to permutate, and I'm going to use all 5 of them. Here I have 5 objects to create a combination out of all 5 of them. So when I'm doing permutations, you can see this right here is 1, 2, 3, 4 different permutations. When I'm permutating things, the order makes a difference. So blue, red, gold, green, purple is not the same permutation as purple, blue, red, gold, green. But, and this goes on, you see I put the 3 dots here because this, I think we decided it's 120. Right? Did we already decide that? That may be in the future. Yeah, I think that's in the future. All right, so here I have however many permutations I can create, since order, every time it's in a different order, it's a different permutation. Now combinations are different. Combinations are, one group is 1. So a group of gold, green, blue, red, and purple, no matter how we move those around, it's still just one group. And a combination, I didn't even mean to do this, but it kind of looks like a combination lock. But think about it, a combination lock order matters. We have to turn that lock in the right order. We can't just put the numbers in any order we want to. So really, rightfully, a combination lock should be called a permutation lock. Why didn't they call it correctly? Maybe the person who created it had some knowledge of combinations and permutations, but not enough to really know the right name. I don't know. All right, so let's look at some permutations. Here I have 5 objects. These 5 objects, if I want to decide how many different permutations I can make out of 5 objects, I see that for my very first slot right there, I have 5 different options of which objects can go into that spot. So I just chose a green one. Now I have 4 options for the next slot. 3 options, 2 options, and 1 left, 1 option there for the 5th slot. Well, this, think about it, how I piled these up here above this gold one. I could have chosen any of those 5 to go into that position. I could have chosen red, and then in the second position I could have chosen green. So we multiply those together, and that tells us how many different permutations we could have. And in this case, I am going to find out that no matter, well, not no matter, but you see each of these different permutations. Pretty cool, huh? each one of those is a different set. All right, so here we have it. We have 120 possible permutations of 5 objects if we use all 5 of them. Now let's look at our formula again. When we're looking at our formula, we see our permutations, we counted them, and now here we're going to break the formula down just a little bit. So right back up here, we can see that, you know, looking right up here at the top part of the formula, each of these variables are plugged in the next set here. So here I had my 5 factorial divided by the number of objects minus the number of objects that I used. I used all 5 of them in this case. So I ended up with 120 in my numerator and 0 in my denominator. But you have to be careful because I know we're used to everything being 0. If it's 0, it's 0. Well, that's not the case when we're dealing with factorials. Because with factorials, we're talking about how many different ways can I arrange 0 items. Well, if I have 0 things, I can arrange those 0 things one way, and that's with an empty set. So even though the set is empty, it's still an empty set. So I can arrange 0 items one way, and that's how I got my 1 in the denominator. So here's the formula broken down. All right, now let's look at this. What if I had 5 items and I only wanted to arrange them? I only wanted to arrange 3 of them. So in this case, I have 5 items here, and I want to arrange those 5 items 3 ways. So I have just had to change just this one number. Well, now I have 5 factorial over 3 minus 2 factorial, which leaves me with 2 factorial. So I'm showing you here how I was able to divide out that 2 factorial. And here you see that I have, I'm actually gonna, let's see if I can do something real quick here. I kind of just thought of this. So let's say that I have this, this formula here. This is the exact same formula. But instead of writing 2 times 1, I'm just going to write this as 2 factorial. And I am going to keep my denominator as 2 factorial. And you might see this written this way, so I'm showing it to you. And you may have already seen it written this way in your homework. So here I have in my numerator 5 times 4 times 3 times 2 times 1. And in my denominator, I have 2 times 1. Well, those things divide out. Now, in this little formula that I have down here, I did 5 times 4 times 3 times 2 factorial, because 2 factorial is the same thing as 2 times 1. So these can be broken down in different ways. I'm just going to go ahead and put this down here. We'll show that both ways there. All right, very good. So let's see what is next. Okay, here it is. If I have 5 items and I want to find out how many ways I can arrange them if I'm only going to use 3 of them. So I have 5 and I'm only going to use 3. And we wrote 120 here. This is incorrect. It's because I just from cutting and pasting slides. So please always keep a lookout for those types of errors. So I have 5 times 4 is 20, times 3, 20, 40, 60. So this should actually be 60. All right, now moving on here, I have 5 items and I want to find out how many ways can I permutate 3 of them. All right, so I have a choice of 5 different ways I can fill in that first spot, 4 ways for the second spot, and 3 ways for the third spot. Well, what about those other 2? Well, they're still out there. I'm not going to use them. They're leftovers. So here, this is how we calculate it. We just looked at this. At least this time I got it right, huh? All right, now, again, we have the same slides. Let's look here. What if I had combinations? When I'm dealing with my combinations, I have to remember that everything's exactly the same as the permutation formula, except that last little piece there on the bottom. You see on the bottom where I'm dividing out a whole extra 5 factorial? Well, the reason that we do that is because we're getting rid of all of the repeats. So say, for example, right here, I have 5 objects and I want to permutate them by only using 3. Well, let's just say I use just the Louisiana colors, the Mardi Gras colors. So I have gold, green, and purple. And I have 5 items, but I'm only going to use 3 of those items. And in this case, I'm showing you that out of those 5 items, if I arrange gold, green, purple, purple, gold, green, green, purple, gold, those are 3 permutations. Where over on the combinations, it's just 1 combination. So no matter which order they're in, those 3 colors are 1 combination. All right, and then the same thing with red, green, and purple. I can arrange those 3 different ways and get this number, and it goes on. I can get more, and then over here I can see that that's only going to end up with 3. I'm sorry, a grouping of 3 is just a single combination. Okay, so now let's see, and if we had 5, same thing here, 5 permutations, 5 combinations, but I think we already looked at this slide earlier. All right, so let's see here. Oh, okay, so yes, I did put that slide again, because let's see, we have this dot, dot, dot. How far does it go? If I have 5 permutations using all 5 items, or 5 combinations using all 5 items. Well, in this case, I actually meant for this to be a 3. Let's check ourselves. We had said that using 5 items was going to give us, having 5 items, using 3 of them would give us 6 permutations, and then having 5 items, using 3 of them would give us only 10 permutations. Because see this 3 factorial down here in the denominator? I can't seem to get it to select that just by itself. But this 3 factorial down here is the 3 that I have to divide those out, because remember, I'm not going to use all of these different groupings. In a combination, it's just 1 group, so I'm literally dividing out the rest of the groups. And that's what the extra piece means on the combinations. All right, I also wanted to show you guys, I'm going to open my Google page here, and I'm going to ask combination permutation calculator. All right, so I have this permutation combination calculator here, and when you guys want to check your work, or if you have some homework, let's just have a look at this. What if I have 10 items, or no, what was I dealing with? 5 items, and I want to use 3 of them. My calculator will tell me I have 60 permutations and 10 combinations. So what if I have 5 items and I want to use all 5 of them? Well, I get 120 permutations and 1 combination. So you guys have a nice calculator that you can use to check your work, and you saw when I Googled that tons of them came up, so you can actually use one of many. All right, let's see what is next here. Binomial probabilities. And when we talk about binomial probabilities, there are several ways to calculate those probabilities. We use formulas. We are going to use Excel, although we're still going to also use our formulas. We're just going to put them into Excel for that Excel to calculate it for us. All right, so let's move on to our Excel. We're going to calculate binomial probabilities using spreadsheets and real-life scenarios. So I will see you guys on Excel. All right, you guys ready for scenario number 2, our Excel portion? So let's have a look at our Excel document. For scenario number 2, we're going to be looking at some binomial experiments, of course, because that's what we just talked about in our PowerPoint portion of this scenario. So let's see if we can believe sources that we trust. For the first part of this, we are looking at a friend of ours who's excited about a party tonight, and our friend knows we have a quiz tomorrow, and we say, oh, I can't go to the party, I have to study for my quiz. And my friend says, oh no, you don't have to study for that quiz. I took it last semester, and I guessed on all 10 questions and scored 80%, so come on to the party with us. So that's what this scenario is saying. And we're going to use the binomial distribution formula, that big formula you just saw, in Excel to calculate the probability of our friend randomly answering all 10 questions with a score of 80%. So our tasks for this are to, and this scenario came right out of the Dave Sebecki, Brian Mercer quantitative literacy textbook. So our tasks here are to list 4 requirements for a binomial experiment, consider the relation between this scenario and the binomial experiment, list the binomial distribution formula in 2 different ways, and then list the value for each variable of the formula, and then we're going to create a table showing all of that stuff. So let's first go over to our, what should we look at first? Let's go ahead. The first thing says to list the 4 requirements. So here I've already set up a chart for us, a page, a sheet. So here I have the binomial experiment, and I listed the 4 things. It has to have a fixed number of trials. Each trial is independent. There are only 2 outcomes, and the probability of each outcome remains constant. And we've discussed that, but let's go and see. The second part of this tells us to consider the relation between this scenario and the binomial experiment. So in that case, I'm looking over here at my relationship. Well, I have a fixed number of trials. On the left, I have the requirements of a binomial experiment, and on the right, I have our experiment that we're looking at right now. So a fixed number of trials, I had 10 of them. And then I had, for each trial is independent, we had four questions, 4 answers for each question, and only 1 of them was correct. So each trial is independent. If I answer 1 question wrong, it does not affect whether or not I answer the next question right or wrong. There are only 2 outcomes. Yes, there are 4 possible answers, but they're either right or they're wrong, period. And then the probability that each outcome remains constant. Well, again, there are 4 possible answers and only 1 is correct. So every single one of the questions has a 1/4 chance of being correct. Now, I just took all of that same information and put it into a chart just to organize it. That's kind of just what I'm used to doing. All right, so let's go back to our Excel here. I have done all of the things required on my document. It said to list the binomial formula in 2 different ways, as well as the Excel command for distribution, for binomial distribution. So then I was also instructed to identify each variable. So I have B is my binomial probability, X-ray, my total number of successes, and in this case it's pass or fail. You know, or if it was a different experiment, it could be heads or tails. The probability of a success, that's what this PAPA stands for, the probability of the success of a trial. And then in the probability of not succeeding is 1 minus the probability of succeeding. If you think back at the rolling the dice, you had a 1/5 chance of getting a 6 and a 5/6 chance of not getting a 6. So you see it's just 1 minus the chance of winning. And then you have N, November, is your number of trials. So let's see if we can, I am going to see what I can do about this. I want to look at both of these at the same time. All right, so now here I am going to plug in my variables. So I had the fixed number of trials. Well, what did X stand for? X is the total number of successes. Well, how many total number of successes did we have in this one? Well, he said he scored 80%. My chart's not really helping me. So the total number of successes here were 8, right? There were 10 questions, 80% of 10 is 8. And then the probability of getting a question correct is, well, there was 1 correct out of 4. All right, and if you guys, if this turns to a date or anything, you know what to do. Select the cell, go up here, turn it into a fraction, okay? Now, what is the probability of not a success? Well, it is equal to 1 minus the probability of a success. And when you guys use your cell referencing, you can come back and use this for your homework and plug in any numbers you want. All right, and then we had the number of trials. Well, how many trials did we have here? Well, we had 10. All right, now we're ready to plug all of this into our lovely formula. So you guys should already have these formulas written out. In your instructions for this, it did say to list the binomial distribution formula in 2 ways. And then it says to create a table to show the binomial distribution formula in 2 ways. This is the table we're actually looking at right now. The Excel binomial distribution command, the calculations for this scenario to 3 decimal places after any beginning 0, and the calculations for this scenario in percentages. Plug in values for each of your formulas and use the Excel command and show that both formulas and the Excel command are equal. So that's what we're doing right now. All right, now I have listed my formula in 2 ways, and I have my binomial distribution command. And you know, when you guys can Google these formulas also, you know, binomial distribution formula. And you can click images, and all kinds of different images come up with formulas. So you can find all different ways to write the formulas for these. Once you manipulate the formulas, they all end up being the same anyway. So back to our Excel. We're ready to start plugging these formulas in. Okay, a calculation here. Now, folks, we have a lot of stuff going on here, and Excel is going to do a lot of this for us because you're probably trying to figure out, how am I going to put this n big CX into Excel? Well, that's called a combination. And you guys remember that in Excel, I get all kinds of cool commands. So I just type in COM, and it comes up with combination. This returns the number of combinations for a given number of items. So I'm going to double click that. It wants to know the number and the number chosen. So I have 8 of these, and I am going to, I have 10 of these, and I am going to choose 8 of them. Okay, that's 10, choose 8. All right, then I'm going to multiply that by P, and I hope you guys can see I'm just following my formula. Raise that to the power of X times, open parenthesis. Now, you guys have to use all of your parentheses here, because if you don't, Excel does different orders of operations for things. So here I'm opening my parenthesis, and then I do 1 minus Papa, close parenthesis, raised to the power, open parenthesis, of November minus X-ray, close parenthesis. And voila, I get an answer. Whether or not that answer is correct, I really don't know right now. I'm going to do all 3 of these formulas and see if I keep getting the same answer, and if I do, I will trust my answer. Now, the second formula is a little more complicated. You see all these parentheses here. Why do you need all these parentheses? Well, look, let me just show you this simple little game we could play, experiment we can do. Remember order of operations? Remember when you have, please excuse my dear Aunt Sally, and we know that that means, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication and division, and addition and subtraction. So when we're using Excel, Excel wants order of operations. So if I do 3 plus 5, actually I'm going to change that. I'm going to do 5 plus 3 divided by 4. 5 plus 3 divided by 4, what do I get? Well, I get 5 3/4. Well, that makes sense. I did 5 plus 3/4, right? Well, what if I use this exact same thing, except this time This time, I put parentheses around my numerator. Now I have 5 plus 3 divided by 4. What do you think that's going to be? 2. So parentheses make a big difference. Parentheses are actually functions in mathematics that we need to use. And that's why we have all of these parentheses. Okay, here we go, guys. We have this factorial. The explanation point does not just work in Excel as factorial. We do have to actually type in factorial. So I'm going to keep all of the same parentheses that I have here. And I've already done this and made the mistake of not using enough parentheses. So I'm going to go a little crazy with them this time. I'm opening I'm just going to follow everything that's on that formula over there. Open 2 parentheses, type in FACT for factorial, double click that factorial there, and then, hold on. Okay, sorry, I had to plug in my other computer. It's rendering our first video and it was just about to die. So now here I have my factorial. Let's get back to where I was. Okay, I do have to go back and delete this because I cannot shrink this without doing that. Right, again, equals double parenthesis, FACT, factorial n. So I'm just going to click this n here, close my parentheses, but then on my formula there, I have another parentheses. So I'm going to close both of those. So remember, you have to use all the parentheses in your formula plus whatever parentheses the factorial function gives you. Hopefully that works for us. Divided by 2 parentheses, and then we have factorial factorial what? It covered up my formula. N minus x. N minus x. All right, and then, okay, I had to delete all of that and go back up and select this formula and paste it down below because it kept covering it up. So just little things that you can do to keep stuff like that from happening. All right, so this is divided by, and I know I've already done this multiple times, sorry guys, factorial. All right, n minus x, n minus x, close parentheses, and I close the parentheses on my factorial function, and I have to close parentheses on that formula that's down there. All right, now that is going to be times x factorial, so that's going to be times factorial of x. Close the parenthesis for the factorial function and then close 2 more parentheses because that's what's on my formula, times p raised to the power of x times, whoops, times q raised to the power, I need my glasses here, times q raised to the power, open parenthesis, of n minus x. Okay, you ready? Cross your fingers. Yes! All right, so we did it, you guys. It wasn't easy, but we did it. Now, the next part is muy fácil, or muy fácil. Help me out, though I'm not sure which one of those is correct, but it means super easy. So here I am going to do my binomial distribution using Excel. So I put an equal sign in here, type in binomial, go to the binom.dist, binomial distribution, and it wants to know the number. Well, the number is 8, and then the trials, I had 10 trials, and the probability of each outcome was 1/4. That was the possible chance of getting it correct, times, or the last thing is cumulative, and that is false. Remember, we always use false in this class here. All right, yay. So now that I have this, I am going to copy these and paste them all over here, which I don't think is going to work. Oh, it didn't work. You know why? It's the proximity thing. See, because these are all chose the next one over. So if I would have used $signs, it would have worked. I can do all kinds of different stuff here. I'm just going to go through and change. I'm going to hold my control button down. No, I'm not. I'm not even going there. I am just going to undo that. So very easy. All I have to do is double click the cell, select everything in it, Control Charlie, enter, and then paste it into the percentage. Okay. Oh, I think I may have just figured something out. When I was struggling with this formula up here, no, that wasn't it. Never mind. I don't know how to do it. All right, so here I am going to select all of this, hit enter, come into this cell, put that all in there and hit enter. And same thing here. Don't forget, you guys, some of you are forgetting that when you're doing your Excel report, you're responsible to go through and click on these spaces to show that you're using these formulas. So while you're casually talking on your Excel report, you should be clicking on those formulas once in a while just to show us that you used them. All right, folks, here we have a 0.04%. That's not 4%. That's 4/100ths probability. Wait, well, that's 4/100ths of a percent. So that's actually one, is that right? 4/10,000ths chance that you can guess all 10 questions and get 80% correct. So when your friend's trying to talk you into going to the party, saying that they got an 80% on the quiz by randomly guessing, you can say, you know what, there's only a 0.04% chance that that's true. You know, it's up to you if you want to believe them. Sure, it's possible, but it is not probable. All right, let's see what's going next. I'm coming back over here to my worksheet. I've completed that whole first part. So now we have learned how to double check information from someone that we trust, our party friend. And now we're going to check and see, can we trust the lottery ticket people? You can't win if you don't play. Is that what they say? This is a scenario taken out of the Dave Sebecki, Brian Mercer textbook. And this is going to give us some information about a $5 scratch-off ticket. And we're going to find out, is playing the lottery worth it? What is the probability of actually winning? Well, this is a ticket here that gives us some probabilities. It looks overwhelming, I know, with all of these numbers and things, but we can break this down pretty simply here. So we see that in this ticket, if we buy a $5 ticket, we have a 1 in 14 chance of winning. If we buy a $10 ticket, 1 in 8.57 chance of winning. If we buy a $15 ticket, we have a 1 in 140 chance of winning, and so on. All the way down to, if we buy the ticket, we have a 1 in 1,334,922 chance of winning 100 grand. So let's find out what the expected outcome is on this chart. We are going to observe the ticket sales that are listed values. Are they actually odds, or are they probabilities? Well, they're probabilities, especially once you get all the way, you know, the bigger the denominator gets, the closer it gets to a probability, especially, well, when your numerator just stays 1. Because decimal-wise, what's the difference between a probability of 1 out of 1,300,000 or the odds of 1 and 1,242,000, or, you know, this is 1,343,922. If I'm dealing with odds, it's 1 and 1,343,921. So the decimal value is so minutely small that even if these were truly listed as odds, they're just probabilities. All right, so we're going to create a table using the odds that are given on the back of this lottery ticket. And then we're going to decide what the expected outcome is, the buyer's outcome, the seller's outcome, and we're going to do all this stuff. So let's just go ahead and get started on that. So here I have created a list of what I found on that lottery ticket. You guys are probably just going to copy my list, which is fine. And let's just talk about this. Well, you have amounts you can win. You can win $0, $5, $10, $15, $20, all the way down to $100,000 on this scratch ticket. So I made one column for the winning ticket amount. A second column I made here to give the outcome of the winning ticket. And then I have the probability of actually scratching off that amount of scratching off to win that amount. So if I scratch my ticket and I win nothing, what actually happened? Well, I actually lost $5, right? And what's the probability of that? Well, it was not listed on my ticket. My ticket did not give me the amount for winning nothing. It just started with $5. So we'll come back to that. You'll see. Now that I could win $5. Well, if I scratch the ticket and I win $5, how much did I really win? Well, I really won $0, right? Because I paid $5 for the ticket, I scratched, I won $5, so I really won 0. If I scratch the ticket and I win $10, the truth is I won $5 because I paid $5 for the ticket. You get it? Now, if I scratch the ticket and I win a whole $1,000, yippee. The real truth is I only won $995, which is fine. I'll take it. Somebody's going to buy me a ticket. I hope I scratch it and it wins $1,000. Somebody buys it for me, then I win the full $1,000, right? I did get a lottery ticket as a gift one time and scratched it off and won $80. And my father-in-law convinced me to go to the casino, which I had never done before. And I went to the casino, and my $80 I was so excited to get back then in my early 20s, with a new family and a baby, that $80 was everything. And I went to that casino and it was literally gone in 20 minutes and I cried. So I've never been a fan of the lotteries and gambling since. So that's probably a good thing for me. All right, so back onto this. If we want to calculate the expected outcome, I have to know all of this stuff. The amount of winning, the outcome that can happen, and the probability of that outcome. So you guys remember the probability of winning $5, scratching off $5 was 1 in 14. Scratching off $10, 1 in 8.7. Scratching off $15 was 1 in 40. And I got all of this information from all of this data on the back of the ticket that's listed right here. Okay? So in order to calculate the probability, I am going to, for the expected outcome, so let's see what we're going to have here. The probability of scratching of $5 and winning 0 is 1/14. And you guys can see, actually, I should have showed you this. Hopefully you haven't gotten too frustrated at this point, that I had to use the apostrophe here to keep the fraction from changing. So here, I am just going to go to the next cell. And in this cell, I'm going to select all of these guys here. And I am going to change it to fraction because I want all of this to be in a fraction. Or I guess I already have a fraction. So this one's going to be my decimal value. I guess I could just leave it a number. All right, so here I just put equals 1 divided by 14. And we're just going to do that all the way down here, except we're going to change our, we're going to give it some more decimals. And some of them are going to need even more decimals than that. All right, so I'm going to actually go down and just enter all of these values. I don't know, can I just do this? Can I just copy this and bring it over here? Did that work? I guess it changed this one. All right, so now what do I have to do? just put an equal sign here. Changed a couple of them, but I guess in the end it seems like it worked pretty well. All right, I'm gonna go through and fix this. I'm gonna pause the video so that you guys don't have to watch me do all of this. Okay, so now I have all kinds of crazy stuff going on here, and you guys probably do too. I have some of my numbers are dates, some of them are giving them to me in scientific notation. So I'm just going to select the entire column, and I'm going to change it all to number, and then I'm going to give myself some more decimals. Because, let's see, some of these decimals look okay, but some of them do not. So I'm going to choose these, because the directions said to round to 3 places after the ending 0. So notice all the zeros on the ones that I have selected. I need 3 numbers to happen after those, to the right of them. So I'm going to just give it some more. There we go. All right. That's just a couple other things is I want to move this over to that side. I just like that better. Okay. Now I am going to, this one, well, what is this one? What we just calculated was the probability of everything happening. What is the probability of all of the different scenarios of getting this ticket? Well, the probability of scratching nothing is the only thing left over. So I'm going to do 1 minus, whoops, I need an equal sign. 1 minus the sum of all of these numbers. 1 minus the sum of all of those numbers. And it's wanted me to close those parentheses. So here I have it, you guys. This is the probability of winning nothing. Look at that. I have, well, let's look at this in percentage before I have too much fun talking about this. Because look at this, it's like a 77% chance of winning nothing. And look at all the other percentages. The highest one you have is a 12% chance of winning $10. So I am going to add all of these up. You know why? I'm checking to see. Because when, here's my auto sum, yay! You see down here where it says 1? The probability of any event occurring is always 100% chance, not over 100%. So if I add all the probabilities together, they have to equal 100%. All right, so I am going to copy all of this. Hopefully it works. I'm going to put it all into this over here. Looks like it worked. I'm going to change that to percentage. Move my decimals over some more places. All right, I am going to choose these last few down here, move my decimal a little more. I'm going to add these up, make sure it adds up to 100%. And it does, which I knew it would since it added up to 1 over here. Now, let's have a look. We have, let me get my little marker here. We have a 77% probability of winning nothing. Well, that's actually of paying $5. We have a 7% chance of winning nothing. That means we paid $5, we scratched the ticket, we won $5, so we won nothing. We have an 11% probability of actually winning, scratching the ticket for $10, which gives us 5. And then look at all these other probabilities. Pretty low. We have an actual 2% chance of winning $20. That's pretty good. They have to throw those good ones in there, or else the people will not keep buying the ticket. All right, now what is expected outcome? What does the expected outcome look like? Well, the expected outcome is going to be the percent. Well, let's have a look. The expected outcome is the amount that you might win, which in this case is in the first row, the amount that we win is -$5. So we actually lose $5. So -5 times the probability of winning, which is about 77%. All right, so the expected outcome of buying that ticket and losing $5, you're expected, if you keep buying enough tickets, like say you bought 1,000 tickets, remember our law of large numbers, how distribution Turns out that's kind of how expected outcome works. The more tickets we buy, it's expected that we're probably going to end up losing $3.85. That's just on the first one. Well, I'm going to apply this formula all the way down. And now I have my expected outcome for each scenario, and then I am going to just add that up. I get negative $1.39. So what's the buyer's expected outcome? Well, the buyer's expected outcome is negative, or well, I could actually just put equals this cell right here. All right, so then what's the seller's expected outcome? Well, the seller's expected outcome is the opposite of that, right? So the seller's expected outcome, the opposite of the buyer's expected outcome. So if all the buyers expect to lose $1.93, well, then the seller expects to do the opposite. Well, in mathematics, -1 means opposite. -1 times anything spits out the opposite of that number. So I'm just going to do that. All right. So now we have that the buyer's expected outcome is to lose $1.93, while the seller's expected outcome is to gain $1.93. So now we want to know, what is the seller's expected outcome if they sell 5 million tickets? So that's 5, 1, 2, 3, 4, 5, 6 times $1.93. So it looks like the lottery commission should gain $9,627,181.59 if they sold 5 million tickets, which I think they sell a lot of tickets. You can actually check. You're actually required to check for this scenario. You are going to, so here you've done all of these things, created a separate table to show the buyer's expected outcome. We've already done all of this. Now, the last piece here you guys are going to do on your own, and it says to use the World Wide Web to find data on how the Arkansas lottery money is spent. So if we're making all this money, how are we spending it in Arkansas? Everybody knows about the Arkansas Challenge Scholarship, which is fantastic, you know, for many people who qualify for that and get to use it. And there are some stipulations for it, but really not too many. But how much of that lottery money actually goes towards scholarship? I want you to find out. So for this one, you're going to use the web. You're going to find out how Arkansas lottery money is spent, and then create a table and a pie chart to show the percentages of where the money is spent. Then you're going to do that same thing for 2 other states. So say you're going to look at where Texas spends their lottery money, and where California spends their lottery money, and where Arkansas spends their lottery money. So do your very best to create those 3 pie charts and find out where the money is going. See who's transparent and who's not willing to hide what they're doing. And then, of course, you guys have your sentences. We always talk about all of this stuff, defining the relationships between binomial distribution and normal distribution. Remember, we talked about the more experiments that we do, the closer we get to normal distribution. Relate the expected outcome from the perspective of the classmate and the lottery ticket buyers. So if you're the classmate and the lottery ticket, between the classmate and the lottery ticket sellers. So this is sellers here. And then describe how understanding expected outcome can help you make informed decisions, and discuss the expected outcome of the Arkansas lottery and clarify how the lottery money is spent. All right, you guys, super excited to see your Excel reports on this one and your pie charts for where lottery money goes. And I will see you guys in scenario 3. Until then, keep being amazing. You rock.